to the February 3rd experimental math seminar at Retakh University. Today's speaker is our very own Professor Volodya Retakh, who will talk about determinant solutions for nonlinear differential equations. As usual, you're welcome to unmute yourself or even stay unmuted if you have no background noise, so you can have some feedback and ask questions anytime. Otherwise, unmute yourself or stay either way. Okay, if there are no noises. Go ahead, Volodya.
All right, so thank you very much for the invitation. So this is, so let me start. So actually 160 years ago, Sylvester discovered just a nonlinear system of linear equations. And so he considered just this matrix, so Wn, which you can see on the screen. Well, depending on this function f, which you can, this is Hankel matrix, this is Wronskian. And so if you take the determinants of these matrices, depending on n, then those determinants satisfy the system of differential equations, of course, nonlinear system of differential equations. Now it's easy to see that if, say, tau naught equals 1, then tau 2, the expression for tau 2 is exactly the determinant of the corresponding matrix, but it's actually for any n, you have this system. All right, now, and then similar equations just maybe later was used by Darboux, and like maybe 15 years later or so. Okay, and then the subject was not very popular until 1967, when the Sylvester equations were sort of reborn as Toda equations or Toda system or Toda lattice.
Did Toda know about it? I was independently.
No. Very few people. No, nobody knew this for quite some time. And
so who realized?
Sorry.
Who realized the connection?
I know how I got this connection. I got this connection from a physicist named Perk. And because when they published the paper on this Toda system, he wrote to me that in fact Sylvester was the first one. But if you will look on, there are, I know, zillion papers on Toda equations, and only just you can count up to 10 papers were mentioned Sylvester.
Okay, that's nice.
So that's this one. And so the subject was basically forgotten and so on. Now in 1967, it was a revolution. And because Toda equation appeared, and I just, they appeared as some sort of Hamiltonian for a chain of particles. And, so basically, it turns out that after some change of variables, basically Toda got a system of Sylvester type. Okay, now just also I have to know that the Sylvester equation can be actually written as a double logarithmic derivative of tau n, but so which is expressed like it's written here. And after this, of course, you ought to be attempting to introduce the ratio of these two determinants of matrices of order n and n minus 1. And then by using just, you can subtract n plus 1 equation from n equation, and basically you get the system of nonlinear equations. like this. And in this form, the system admits non-commutative solution. And so let me explain what it means. And let me recall that if I have an algebra over a field, and I have then D is a linear map, then D is called a derivation if it satisfies Leibniz rule, which is actually, of course, written here. And now this system can be replaced by a more general system, which is written here. And so this is d theta times theta minus 1. This is sort of an analog of a logarithmic derivative. And then, not surprisingly, you have this system. Now, in this system, one can find formulas for theta n, which I will do now. But for this, we need actually a replacement for determinant. So the replacement in the non-commutative case. And such replacement, well, actually, this is a special case of sure complement, but so now we call it quasi-determinant, and it looks like this. Suppose you have an n by n matrix, just over a ring, and then let's denote Aij, and its submet n minus 1 by n minus 1 submatrix that obtained by deleting the ith row and j column, and then let R sub I will be the row matrix where so index of index I, Aij is removed here. C is similarly a column. And we define just a quasi-determinant of A by this formula. And if this matrix is invertible. And so let me just explain what's going on. So you have this matrix, and you have this special element boxed, which is boxed here. Then you take Aij, then you take this row, the row containing Aij. Without Aij, it's R sub I. You take column containing Aij with without Aij called Cj, and then when you cross the row of index I and the column of index j, you have matrix Aij, and if this matrix is invertible, then you have just this. Okay, and so let me just connect it with the things that we already know. So first of all, that basically the idea is that you take elements of inverse matrix, of the inverse matrix, if it exists, and then take the inverse of this element, and then you have the corresponding quasi-determinant which is written here. And if R is commutative, basically you have the ratio of the determinants of n by n matrix to the determinant n minus 1 matrix, well, up to a side. And now I agree that this is an ugly definition. My only justification is that it works. And in particular, if R is a division ring with the derivation D, and theta n is defined like this, so the same Sylvester matrix, but this element, which is southeast elements is boxed. And so if this element is defined, then actually 130 years after Sylvester, so Gelfand and I, we proved that those theta n, that they satisfy the non-commutative version of the Sylvester-Toda system. So that's, again, let me show you the system. It's here. Okay. Now, actually, again, maybe I have to let me remark that this actually, this notion of quasi-determinant, Vronsky quasi-determinant, appears quite useful in non-commutative integrable systems. Let me just show how it works for a very classical problem.
Can I ask a quick question?
Yes.
So in the non-commutative version, the entries F, should we think about them as matrices or coming from an algebra?
You can as an example, you can think of them about as matrices.
Thank you.
Okay, yes. Yes. All right, now let's, for simplicity, R will be division algebra, D will be derivation, and I'm consider such a differential operator P of D. And suppose I know its solution. Then the question is when this operator can be equal, can be written as a product of these differential operators of the first order. And again, this is interesting because in the commutative case, such problems was considered and was solved by an Italian mathematician Mamuna, and this is a little bit less than 100 years ago. Then again, it was completely forgotten, but when people started to do this modern integrable theory, maybe after like 40 or 45 years ago, such factorizations were discovered, and they were called Miura factorizations. Well, again, the original paper was completely forgotten. Now, this factorization also can be done in the non-commutative case. So again, you have just, suppose you have functions, if you have I functions, f1, f2, fi, then you may have this Vronsky matrix, and you may take the quasi-determinant of this Vronsky matrix. Again, this is southeast corner defined, so the quasi-determinant, and then you can write this factorization in the non-commutative case by using basically logarithmic derivative of this of this quasi-Vronsky. But by the way, in the non-commutative case, the formulas are not any better. You just replace Wi as a ratio of two Vronsky. So the big one and the other one when you omit the last row and the last column. So, but this was, okay, so, okay. All right, now let's go to generalization of Toda lattice. Now, and so generalized Toda lattice was considered like by 5 Japanese mathematicians. So the name is here. And they just consider it generalized Toda system. So from this, the Sylvester Toda system, it's different in the following way. You add this term minus phi times psi times psi, but whatever you pronounce. But what is interesting that in this case, so the system depends on n, so it goes into both direction, into for positive n and for negative n. Okay, now their solution was actually non-trivial. So here so they started with this phi and psi here, and they constructed new elements. So the formulas are here, which depends on phi and psi. Then you may consider these determinants of Hankel matrices. So this is tau naught is 1, tau n is defined by this formula. So this formula shows that basically you have Hankel matrix. So this is the elements on anti-diagonals, they are the same. And so you can consider the corresponding Hankel determinant for n greater than 0 and for n less than 0. And they satisfied this generalized Toda lattice. Their proof is rather technical, but still. Now, why to consider this system? Well, as I said, first of all, it goes in both directions. Well, for positive n and for negative n. And but they noticed that the solution of this system are related with the solution of these Painlevé equations. So I will maybe consider now only so-called Painlevé 2 equation. Now, Painlevé equations are just the famous, there are 6 Painlevé equations, and which are just highly nonlinear differential equations, which studies very actively. They have very interesting singularities and such, and so on. And this is actually formula for this Painlevé 2 equations. Painlevé 2 equation, as you see, it's a nonlinear U cube here. And well, so it depends on the constant. Well, different people writing this constant very differently. So let me follow to this Kajivara and Masuda. So they used this scalar alpha plus 1 over 2. And they showed that if these functions phi and psi, which are here, they satisfy so this extra differential relations, so which you can see here, then the ratio gives you a solution of this Painlevé equation. So you are getting determinant solutions of this non-linear equation. Okay, now it's since you have, whenever you have a ratio of 2 determinants, you are always tempting to consider sort of quasi-determinants and to have a non-commutative version. So let me start with the non-commutative version of this system, this generalized Toda system. And so this was done by Vladimir and me. So I will use notation. This is D is just an abstract derivation. Well, I will use df equals f prime. And I will consider now this system that is basically similar to what Kajivara and others were doing, except that it is written in a symmetric way. And this is actually somehow an advantage of non-commutative approach. All your equations, they become symmetric. Okay, and so this is the system. So again, this is symmetry because psi and phi are inside those products. Then you may consider Hankel matrices as it was done before. For these Hankel matrices, you take the corner quasi-determinants. Again, that's the same southeast corner. And if you define those numbers, then you have exactly this is the Toda system for theta n and for eta n. So exactly that, so it's generalization of what was done before. And so please note that the ratios for positive n, you can write the ratio, so the divisor sort of from the right, and from negative n, you write the divisor from the left. Okay, now you're attempting to write non-commutative version of this Painlevé equation. Well, as I said, that so the advantage of the non-commutative brings symmetry, and this is a non-commutative Painlevé equation. So you see that instead of 4xu, you consider 2xu and 2ux. Now, you don't know actually what this variable x is. All you need to know that the derivative of x is 1, and alpha is a scalar, and the derivative of alpha prime is 0. So to this one, and then you have this generalization of this Kajivara theorem. So if you impose extra connections on phi and psi, then you have just Toda solutions of this Painlevé equation. So non-commutative Painlevé equations. Again, this is the equation. Now there is a funny thing.
Yes. So the alpha x and alpha and u are formal non-commutative variables.
Yes, yes. They're formal. No, alpha is a scalar, alpha is commutative.
Alpha is a scalar. But x and u.
Alpha is a scalar, which is commutative. X is just any variable such that x prime equals 1.
So can you have a power series solution in the beginning? Can you expand a u as a power series in x?
Oh, yes. Well, okay. If so, if x is a variable, I can expand this.
Yeah.
But now it's actually there is surprisingly that when this paper appeared, then just an expert in mathematical physics told us that he does not like it because x is actually time. For him, x is time. Time is commutative, so x is must be commuting with u. Even if you consider a matrix version, x must be just a constant matrix. And then immediately after that, it was a paper on Painlevé equation connected with the matrix sort of Hilbert problem. And in that case, X was just a diagonal matrix. So there were no commutativity here. All right, but so this is just this connection. Now, I would like to talk maybe about a connection between Toda equations and orthogonal polynomials. Okay, let me remind you this classical stuff. So you have just, if you have a measure, a good measure, then you can on a real line, then you can define moments. So C sub I just by using this formula, this is x to the I, x is just a variable here. And then you define polynomials, which I wrote in this as a quasi-determinants. Of course, people do not write this classically. People do not do this. They take the determinant of this matrix, and then they divide this by the determinant of this n-1 of a smaller matrix, such that you remove the last row and the last column. And they do this because they want to have just coefficient for x to the n equals 1. All right, and then again, very classical stuff. You know that these two, if you integrate these two, this product by this using this measure, then it's equal to the integral equals to 0 if m is not equal to n. This is the condition of orthogonality. And there is also a recurrence relation between the three orthogonal polynomials. And there are formulas for coefficients a sub n and b sub n, which I will not present here. Now, where is Toda system? Okay, now suppose I will replace this measure by mu of x. So I will multiply this by e to the tx. Then everything depends on t, including coefficients a and b. And one can write this formula. So, and one can get then this system for this, for an prime and bn prime. Okay, after you introduce t here. And basically, some people call this also Toda system. And this is because after the substitution, which is not surprising for you, we saw this expression when we were writing Toda system, that if you just do this substitution, you arrive to the Toda lattice that that was described in the beginning of my talk. Okay, that's classical thing. So some people actually, again, proclaim that this is just the real Toda system. And then you can find a sub n and b sub n, then you use these recurrence relations to define your polynomials, and then you can find the measure mu that just will give you those moments and this expression. It's pretty classical stuff. By the way, Doran, you asked if this is just, if somebody is mentioning Sylvester. Actually, a paper that I saw on this matter, they mentioned Sylvester, but the reference was not to the original paper, but to the book by Carlin, and Carlin also quoted Sylvester, but also without reference. Yeah, but the reference, okay, so okay. Now, again, you have this expression, and you see that this is quasi-determinal form. Then you're attempting to do non-commutative analog. And you can do this actually in two ways. The most general case was considered in the paper by the so-called hexagon papers by 6 authors. And the idea was that let's start, so suppose you have a ring with an anti-involution, and with R goes to R bar, and you define scalar product between polynomials by using just this pairing. So basically, you have to pair alpha x to the I and beta x to the j. Sorry, the j here must be as a power. And then you have just this formula. You're writing alpha I. There you insert the moment of the index I plus j, and then you take the b b bar of this. Then you can construct these polynomials as above, just by using this formula. And notice that basically those guys are orthogonal. Those guys are orthogonal, and you can find also this analog of this recurrence relations just by writing formulas for A and B. Okay, so there's a disadvantage of this. You don't know how to insert T here, how to make coefficients depending on T. So there is actually a less general approach, which was actually done by, well, there are different people who done this. Let me just use, this is just a dissertation of the former student of Grunbaum. So just, and this is from Berkeley. Now, again, I recall that Crane or Crane, depending how you pronounce the name, considered metrics orthogonal polynomials. So basically, he considered these orthogonal polynomials over Hermitian matrices. In this case, the advantage is that you can introduce the measure. And so by using this weight function W of x, which is just a Hermitian matrix depending on x. Then you can define everything, moments, as it was, orthogonal polynomials, and find coefficients A sub n and B sub n. But when you have the formula for the measure, you may insert an infinite set of time variables into this measure by using just this formula. So this is E, this is exponent of this series, and I here is just K by K identity matrix. So we have this new matrix. And you can compute A sub n and B sub n of t, as it was before, and to check that they satisfy this system of equations. And just again, this non-commutative effect is that here you have A times B minus B times A. So this is effect. And this can be interpreted as a non-commutative Toda system. And basically you can go this back and get a system like it was before. Let me just draw. Okay, okay, that's the system. Sorry. Okay, that's the system. All right, and okay, and so maybe I will stop here. So just okay, it's and again a little bit my experience with talks using quasi slides, but so I will stop here. Of course, could of course add more about this stuff. But
so thank you. Let's thank Volodya, and we have time for questions.
Yeah,
So I have
can
some
I ask a
questions.
quick question?
Yeah, go ahead, Eddie.
So in the hexagonal paper, the one with 6 authors in the first approach, what is the role of the anti-involution?
Just to have this, sorry, let me just, okay. Okay, well, when you have this pairing, and usually people do pairing in the complex situations, and then always you appear just a conjugation. So this is sort of a non-commutative version of the conjugation.
True.
Okay.
So Volodya, in this time variables, does it have any physical significance? So you have so many time variables?
No, and this is actually unfortunately because actually several results that were obtained again somewhere between so this is so this is just maybe approximately 100 years ago. There were results on actually on differential operators, of ordinary differential operators that were actually forgotten and then rediscovered again when people became interested in integrable systems.
And the dissertation of by a student of F.A. Grunbaum, it was a commutative case that you made a non-commutative analog, right?
No, that's no. Grunbaum actually did so actually worked with nonlinear equations. Now Grunbaum actually worked so well with just a classical case, but as well as a matrix case.
For matrices, right? So
yes, for matrices.
But you did it completely non-commutative. For you, it's completely non-commutative?
No, yes, what we did was completely so non-commutative again, but we sort of consider this as a so application of our technique. Now, this paper is actually, I believe, more than 100 pages long, and it's called non-commutative symmetric functions. So,
yeah. Also, you did make, yeah, that's one of the things you did. Yeah, it's a famous paper. Remember? Yeah, that's fascinating. But the AN and BN in your theory are everything non-commutative, right?
yes, they're non-commutative, and the formulas are given again via quasi-determinants.
Yeah.
So they're sort of quasi-determinants. Somehow it's related with non-commutative Schur functions, but I wouldn't go right now into this. Yes, but the
yeah.
Yes.
Interesting. And you mentioned Klein. I remember Klein did some seminal work on the generalized string eigenvalues and the whole of a general arbitrary string. Is it related to this? Also, they had moments.
Yeah, well, I know. So Klein was actually exactly, but Klein was a great expert in function analysis.
Yeah.
So just then, so that's probably related. And then okay, so that's
yeah, interesting. Any other questions or comments?
Yeah, I have a question. So, as I understand it, the Toda lattice is somehow mirroring what's going on with this Henkel determinants and this theory of moments. Is there some sort of moment interpretation of the generalized Toda lattice that you mentioned a third of the way through your talk by those Japanese mathematicians?
No, I don't. I am not aware of this. So I'm not aware of this. But also, I looked and this and some works by actually experts with orthogonal polynomials. Again, there are several papers when they start with this system. Just system, and then develop some theory of orthogonal, some type of orthogonal polynomials.
I suppose I'm wondering if you multiply the measure not by e to the tx, but some other function of t, if you somehow.
So again, it's quite natural approach, and somebody probably did this, but I don't know this.
And one other question is can you find solutions to your non-commutative Toda system in the space of quantum determinants, in the sense of
yes, well, yes, absolutely. I can specialize. That's always the case, that you do pure non-commutative stuff, and then you can specialize.
And
because I can explain you how quantum determinant is actually can be naturally defined by using pure non-commutative definition.
And do the solutions you get for the Toda system in the realm of quantum determinants, do they tell you anything interesting? I mean, do they reflect something about the quantum group, which is nice, or? I mean,
so we can actually get the results that were obtained in quantum case. For example, as a corollary, we can get, say, quantum Painlevé equation, and so it's possible, yes.
Okay, thank you.
Any more questions? Well, let's thank Volodya again for a great talk.
Thank
hope
you.
to see you next week. Thank you. Bye-bye.
Okay, bye.
Professor Retakh?
Yes.
Could I get a copy of your notes here?
Yes, just send me, you can send me an email and I will just send it to you.
Anyway, they'll be posted in the seminar website.
Oh, okay, as long
hopefully.
as they're going to be posted somewhere.
Also the video.
No,
will be
but
posted.
the talk, but I can send you the notes. So
I'll send you an email, yeah.
if you send me an email, I will send you notes. And so,
Okay.
But Volodya,
but
also
I
please send me
can
the slide.
also maybe give you just references to papers that mentioned here.
Okay, well, this actually, I like the presentation, so it would be nice
All right,
to.
okay. All right, okay. Okay.
Thank you.
Okay, welcome. Yes.
All right, bye everyone. See you next week.